Today I'll be talking about developing applications, how to simplify application development using SoC FPGAs. I'll start by discussing what we see as the main challenge in using these SoC devices, and then how high-level synthesis can help in the development of applications. I'll show this with an example and a little video at the end to see the example in action. Just to clarify what I mean by SoC, I mean a RISC-V processor attached to an FPGA fabric. And the main challenge is that you need software and hardware skills to develop for these chips. And there are many moving pieces in both domains. The languages, the tooling required for hardware development may be unfamiliar for software developers, and software development itself could also be quite challenging. I've worked in projects where people prefer to change the hardware than to change the software. So there are companies that can have dedicated teams for hardware, a dedicated hardware team, a dedicated software team, but there are many documents, frequent meetings to avoid misunderstandings, and that becomes an overhead in the development process. And not all the companies have the luxury of having different teams. Like startups or small teams, it's sometimes the same team that has to do both, and sometimes even the same person. And then on top of that, we see there are more software engineers than hardware engineers. And quite often, software engineers are waiting for hardware developers to deliver the hardware so that they can develop and test and validate the software on top. So the question becomes, how do we make hardware engineers more efficient, more effective, and deliver hardware faster? But at the same time, how do we enable software engineers to create their own hardware and not need to depend on the hardware engineer all the time? And just to qualify in terms of software, there are different kinds of software engineers, and there is front-end developers, more like web-based. They are abstracted away from the hardware, but embedded programmers are pretty good at understanding the underlying hardware. So we believe that by using C++ as the lingua franca, a common abstraction between hardware engineers and embedded programmers, and high-level synthesis tool, we can accelerate the development of co-designed systems with software and hardware. So if you're not familiar what high-level synthesis is, it's a concept that has been out there quite some time now, but it's basically taking a function written in C++ and the compiler can generate a Verilog for you. But it has been evolving over time, and now modern HLS tools generate also integration scripts. So not just generate your accelerator, but also integrate it automatically into the system. A lot of things can go wrong during integration. And also, another way to simplify the development process is to auto-generate software API such that the processor can control the accelerators. A lot of bugs that I found in my career is because this manually written software API becomes out of date, out of sync with the hardware. So the contract between hardware and software can be auto-generated now and eliminate that possibility. And also there is from the same C++ description, part of the C++ is compiled by the RISC-V processor, by the RISC-V software compiler, and part of the C++ code can be compiled and run on the FPGA fabric. This is the so-known partitioning. At the moment, SmartHLS, which is Microchip's high-level synthesis tool, supports the quad-core RISC-V processor in Microchip's PolarFire SoC devices, which is used in the example that I'll show you in a bit. But we also support the automatic integration of accelerators into soft-core RISC-V processor on the FPGA fabric. So let me show you the example. So this is an application node that another team developed. It has a camera that has video frames going through a series of transformations written in RTL, and eventually they get H.264 encoded and written into DDR. Once in DDR, the RISC-V processor, which is run in Linux, uses FFmpeg to encapsulate the video frames and send them as Ethernet packets that you can see in your laptop in a video viewer. There is also a web browser with a GUI that you can control the pipeline. There is a web server running on the RISC-V processor, and so this is an application that works right now. So now the question is, how do we enable a software developer to include additional transformations in that pipeline without having to depend on a hardware engineer? for example. So we have these foo, bar, bas, cooks functions that were written in C++, and you can start running them on the processor. Then you can offload them to the FPGA fabric. You can add one function, then two, then three, change your mind. And automatically, we also generate an AXI interconnect that allows these accelerators to be accessible by the processor. So if we zoom in now into this HLS video pipeline, if we zoom in, the example has two data paths. When the video frames can go through DDR and in a frame buffer such that the processor can perform the video processing itself. And the other data path is through the series of HLS transformations. All these modules perform different transformations. You can see the impact of each transformation on the original image. And so there's two paths. The idea is to show collaboration between the CPU and the FPGA fabric, but also comparison in terms of performance. The RISC-V processor also uses OpenCV to load some images that will be used in the video. So this, just to give you an example, I'll talk about a little bit the first and the last transformation, to show you some code. What I want to highlight here is that with only a few lines of code, you can achieve very complex functionality. Like in this case, for example, the function is called getFrame. This is the one that steers the video frames either to DDR memory or sends it downstream to the next module. And you can see, for example, here it says if enable, which is an argument of the function, then loop over the number of pixels, which is also another argument of the function, then read the input stream, the pixels coming from the stream, and write them to the memory buffer. The memory buffer is just a pointer, another argument to the function, which is a pre-allocated buffer by the CPU. And it's telling the module where you want the frames to be stored. Now, if this transformation is not enabled, then just read the pixels of the input stream and just forward them. And this is not pseudocode. This is the entire code that you need, and it's all written in C, to create this hardware module. Now, the put frame is the opposite transformation. Instead of writing to DDR memory, it just reads from DDR memory. This is the watermark function. Another function comes after. In this case, the RISC-V processor uses OpenCV to load these Microchip and RISC-V logos and performs alpha blending on top of the video frames. But then again, it's the same concept where only within a few lines of code, you can have this sort of complex functionality. All these pragmas here that you see here in the function basically are just hints to the compiler to tell how you want the hardware to be generated. And just to give you an example, this one, for example, the AXI initiator, this is telling the compiler, please include like a mini DMA inside so that you can burst transfers into DDR memory with just one line. Now, if we have multiple functions, like if you were doing this in RTL, you would have to use things like system verilog or VHDL to make the connections. But we can do this with Tickle using tools like Smart Design. This is like a GUI integration like schematic, and Tickle, you can automate the connections for it. But in C++, basically the integration is just arguments. You use, in this case, the subble filter uses a FIFO between the subble and the invert, and the argument of one function, the output argument of one function is the input to the next. And it is just regular C++. And this argument basically translates into FIFOs or wires or registers. So this is how you can actually perform integration. So for example, in this case, the foo function with this pragma, we're telling the compiler, I want this function to become hardware. Then from the processor perspective, you have two options. You can just call the function as is. The compiler will instrument this function and call the accelerator on your behalf. But if you want to have more control, you can use the auto-generated API driver for you. And then you can just set up the function, write the arguments to it, start the accelerator, and while it's busy, you can do something else, or you can just wait for it to complete. So this is in a nutshell what the abstraction looks like. And obviously, the software in the example is a little bit more complex than that because there is a web server running on the RISC-V processor. There is a web browser, and there is JavaScript that reacts on events. So when you click the start button, the stop button, you'll see that in the video. There are scripts that start the main application that controls the accelerators. There is some function that writes all the arguments in the GUI that get written into the flash storage device. all the options, and then it starts FFmpeg for the encapsulation. And then the processor also computes the frames per second and makes it available in the GUI. This is the main application that controls all the accelerators, and roughly this is the pseudocode that goes in the application. There is a setup for every accelerator, and then there is a main loop that has a keep going variable, initialized to 1. And for every iteration, it reads the configuration in the storage, writes the arguments to the modules, start each accelerator, wait for it to complete, update the frames per second, and then loop again. Then there is a signal handler that when the user clicks on the stop button, it sends a signal, changes the value of keep going, and then the loop terminates. That's as simple as, that's the overall application. And then there is the FFmpeg plus the Linux video driver that takes care of the other non-HLS generated modules. Another feature of high-level synthesis that allows, that simplifies the development is the concept of application main versus test bench main. So you can have your main application that talks to all the different accelerators, but you can also have like these mini mains, or what we call test bench mains, that can let you help in the development and verification of each one of the transformations, so that once they're ready, then you can just include them into the main application. It's sort of like a divide and conquer approach for validation. But let me show you a quick video of the example. So here is the GUI that has all the controls. This is Wireshark. It's a packet capture. I'll show it to show the bandwidth usage of the Ethernet bandwidth. And below there is the secure shell session into the board. You can see the four RISC-V cores. And then I started the video. The video has a YouTube video playing in a screen in front of the camera and a digital clock. And you can see right now that we have around 33 frames per second, and the processors are pretty much idle. They're not doing anything. All this video is going through the FPGA data path, not the processor. So it's being computed by the FPGA. And I enabled the pixel inversion transformation, and we got in real-time pixel inversion. The frames per second is the same, still 33 frames per second, and the processors are pretty much idle. The CPUs are not doing much. Then threshold to 0, basically all the pixels below the threshold get 0 out. The brightest pixels survive. And then I increase the threshold, the image gets a little bit darker. The frames per second is the same. CPUs are not used. This is Sobel filter, typically used in edge detection applications, being computed in real time. There is a little bit of a usage here for the CPU, but that's not because of Sobel. That's more related to the networking stack, and I'll show you it at the end, where that increase in usage comes from. This is the watermark that I told you about. So the RISC-V processor loads that image, and then the hardware accelerator brings it in and performs alpha blending on top of the video frames, and it's the same frames per second, the CPU pretty much not doing anything. And then the rotozoom is a transformation where the processor computes the amount of rotation, the level of zoom, send those parameters to the accelerator, which performs then cropping in the middle and stitching all the images and performs the rotation. And the same frames per second. Now I enable all the transformations at once. And I get an image like that, not very useful, other than just to show that the same frames per second apply. It still remains. It is a streaming solution, and it doesn't matter how much we add transformation to it. The processors are pretty much idle, except for this one processor that is doing the networking stack. Now I'm going to stop the video, and then I'm going to change the path. Now the video frames are going to go through DDR memory, and it's the processor who is going to be performing the video processing. In this case, the CPU also performs a little bit another transformation, which is loads Microchip logo, and it just bounces around the image. And this is the RISC-V processor doing the video processing. Not bad. It's not 33 frames per second. It's 28, 29. Not bad. And it's pretty much idle, actually. It's not doing much. But the moment I enable the pixel inversion, though, you can see now the CPU usage goes really high because it's a multi-threaded implementation. The frames are divided among the 4 processors. And you can see the Microchip logo starts slowing down. It's only 6, 7 frames per second. And then I enable the threshold to 0. slightly more complex than the pixel inversion, but this one is not parallel. This one is just one processor doing the entire processing, and you can see now the logo barely moves, and the CPU utilization is 100%. I won't even run the other two transformations because they're even slower. But then I'm going to show now the Wireshark. And even the frame rate drops to below 1%, even takes a little bit of time to update. When I switch to Wireshark, then we see the bandwidth to go from 2.5 megabytes per second to 10 megabytes per second. But as I go through the different transformations, there are spikes in the bandwidth. This is the Rotozoom, Sobel, and when I enable them all. And this increases in bandwidth is because H.264 is a variable bitrate encoder. And depending on the contents, on what you're compressing, what you're encoding, then you will have different bandwidths. So in summary, what we believe is that by using high-level synthesis and C++, it can be used by both software and hardware engineers to, as a contract, to facilitate the contract in this co-design development. It supports RISC-V processors and FPGAs, and the idea, the concept is that you can architecturally explore and let each do what it does best. Right? We wouldn't be able to use the web server, for example, on the FPGA, right? Or the FFmpeg conversion. So high-level synthesis tools have been evolving over time. They have come a long way, and they will continue to evolve as more systems become more and more integrated, raising the level of abstraction. And this example code is available at GitHub. The idea was not to do the best pixel inversion algorithm. It was just to keep it simple so that you understand the overall flow, and then you can download it, remove all these transformations, and put your own. So feel free to download it. If you have any questions, if you want to follow up, send me an email, reach out, and I'll be happy to follow up. Thank you.